So now let's sum up our comparison between ionic and covalent bonds and ionic and covalent compounds. There's a link here. I can take you through a tutorial, some animations on bonding. And I've also got a link that'll take you to quick animations for each type of bond. Click on them. The visuals really help. Everything that I draw on paper is great, but it's not the same as these. These animations are terrific. Otherwise, I wouldn't put them in there. So we'll start with ionic. And we said earlier that ionic bonds involve the transfer of electrons. In this case, we would have sodium losing its electron, the metal losing its electron to the more electronegative nonmetal. There's a complete transfer of electrons, in other words, a change of ownership, versus covalent bonds, in which electrons are shared. In this case, the oxygen is going to share its valence electron, and hydrogen will share its valence electron with one another in both these cases. Neither oxygen nor hydrogen give up ownership or gain full ownership of electrons in this case. They both share valence electrons, and that's how they achieve a full octet and a stable electron configuration. One other thing to remember, whenever bonds form between atoms, the atoms of each element attain a noble gas configuration. The noble gas configuration for chloride is the same as argon, right? Because it gains one electron, so it would be the period 3 noble gas argon. Sodium loses an electron to gain the electron configuration, the noble gas configuration of neon, the period 2 noble gas, the one before it. Over here, hydrogen would sort of partially gain an electron in this shared bond here, in these shared bonds. So the H becomes like helium, right? The period 1 noble gas, and oxygen would gain 2 electrons, gain partial ownership of 2, to become the same configuration as neon. So everything bonds to achieve a noble gas configuration. Now, the physical properties, a comparison between physical properties. One, we'll start with high melting point and boiling point of the ionic compounds. And the reason that melting point and boiling point is so high is because of very strong chemical bonds. What you have with an ionic compound is Na plus, Cl minus, Na plus, Cl minus. And there's just alternating positive and negative charges, and they're bonded very tightly to one another. In order to melt or boil a compound that's ionic, you have to break those bonds, at least temporarily, and allow for the movement of the different atoms to occur. Because you have to break bonds in order to do that, ionic compounds have really high melting and boiling points, as opposed to covalent compounds, which have very low melting point, boiling point. The reason for this is that in order to melt a covalent compound, you don't have to break bonds. All you have to do are overcome weak IMFs. And what IMFs are, we haven't covered this yet. We'll do it at the end of the unit. Okay, we'll look at a molecule of oxygen here, or I'm sorry, water, and another over here. And what happens is you have discrete or individual molecules. You have one water molecule, you have another water molecule, and they basically interact with each other. They're not bonded. There's chemical bonds inside here, in between hydrogen and oxygen, okay? But the interaction between water molecules is very weak. They do stick together. That's why water at room temperature is a liquid. But when you think about it, the melting point of sodium chloride is about 801 degrees Celsius. That's an ionic substance. The melting point for water, is a cool 0 degrees Celsius. Right? It's a big difference, and you're going to find a similar contrast whenever you're looking at an ionic versus a covalent substance in terms of melting point and boiling point. The second physical property is that ionic substances are electrolytes, which means they conduct electric current when they're in solution. So it conducts electric current in solution. When you dissolve sodium chloride in water, it will actually make the light bulb turn on in the little demo that we're going to do this week. So when a substance dissolves in water, which means it becomes aqueous, if it conducts electricity, it's called an electrolyte. On the other hand, you have covalent compounds. They are non-electrolytes. If they do dissolve in water, which they usually don't, they won't conduct electric current. Sugar is an example of something that will dissolve in water, but it won't conduct a current. So that means that covalent substance is a non-electrolyte. And then the third is that, simply stated, again, because of the bonding in ionic compounds, they're very hard. And it's because of the strong bonds between them, covalent substances tend to be very soft. All right. The last thing I wanted to mention, in addition to conducting current in solution, the ionic substances will also conduct electric current as liquids if you melt them. It's just very rare to have molten, salt or molten ionic substance at 800 degrees conducting current. And the last part on this chart is just comparing the electronegativity differences and giving you an idea of why there's a complete transfer, why one element ends up with complete ownership of electrons in an ionic bond, and why that doesn't happen in a covalent bond. If you look at the electronegativity of sodium, it's very, very low, like most metals. The electronegativity of chlorine is very, very high, the lowest being 0 possible, the lowest recorded being 0.7 for francium, the highest being 4.0, which is fluorine. So chlorine's pretty close to that. Because there's such a huge difference in electronegativity, chlorine will rip the electron away from from sodium, forming sodium chloride, an ionic compound. When you look at this covalent compound to the right, you have water, you have oxygen at 3.5, you have hydrogen at 2.1 each. So the electronegativity difference between the oxygen and each of the hydrogens is only 1.4. It's actually kind of high for a covalent substance, but it's much, much lower than the 2.3 we saw over here. So the last thing we'll say here is that the greater that electronegativity difference, the greater the percent ionic character. It doesn't mean that with a great electronegativity difference you automatically have an ionic bond. But the bigger the difference, the greater the ionic character. Okay, so the farther apart the electronegativities are of the two elements bonding. The closer the electronegativities, the greater the covalent character, until you get all the way down to a 0 difference, like when you have a diatom. Diatoms, like oxygen, have identical electronegativities. 3.5, 3.5. There is no difference, so it's a perfectly equal sharing. That is the epitome of a covalent bond.